So, good afternoon, everyone. So we'll start today's session on our discussion for week 4. My name is Adyasha Sahoo, and I'm a PhD scholar at the Department of Electrical Engineering, IIT Roorkee. So, for today, similarly, we'll see the key concepts that were discussed in this week, and then we'll solve the previous year assignment followed by your doubts. So, in the previous week, we derived the coefficients for reflection and refraction for voltages and current. And also, we saw the special cases where the line was terminated with a short circuited line or an open circuited line. So, those all things we had seen. For this week, similarly, we will see when a special case and derive the formula when the line is terminated at a T junction. So what we mean by this T junction is basically, let's say this is your line, overhead transmission line, this is your OHTL with characteristic impedance ZC, or for lossless line, which will be same as your surge impedance ZS. And this line, it is terminated at the junction with two other lines or two other different impedance lines, we can say. So let's say this is uh, ZC1. So this is ZC1, this is your ZC2, and let's say we are assuming here that both of these lines are having equal impedances. So earlier week what we had seen that this we had a single line basically. Previously we had seen that there was one transmission line OHTL which was terminated by either one Z load with certain impedance, or we had seen cable, or simply it is open circuited line, or simply it is a short circuited line. So these all cases we had seen previously. So today what we are seeing is when this is terminated by two lines of impedances. So firstly we will see for equal impedance, and in general then we will see what will happen if these impedances are different. So this is your ZC1 of the line, this is your characteristic impedance of your line, this is your characteristics impedance of line, and ZC2, ZC2. So let me, where is that? So these all cases we had previously seen. Today we will see another special case. So let's say, let me remove this also, this diagram. So this is your characteristics impedance of line, and these are two other lines. So let's say this circuit is, let me close the circuit now. And this will have a voltage source here, and we have seen that this magnitude is 2 times the forward voltage, right? So let's say, so earlier what we had seen for the transmitted voltage, we transmitted, so transmitted is in this part, right? So this is your transmitted. That was 2VF by ZC1 plus we had earlier I was calling as Z load or ZL multiplied with ZL. So if you see this effective impedance Z load, if I represent these two lines as Z load, so this is equivalent to two lines connected in parallel of impedances ZC2, ZC2. So this can be represented by an aggregator or equivalent load of impedance ZC2 by 2. So here if I basically replace Z load by ZC2 by 2 for our case, this case, so I will get for this case the transmitted voltage, it will come as 2VF ZC1 plus ZC2 by 2 times ZC2 by 2. Let's say if this was connected with impedances or line with impedances ZC2 and ZC3. So what will happen is your Z load will be parallel combination of these two lines. So ZC2, ZC3 divided by ZC2 plus ZC3. And in place of Z load, you can substitute this value in this formula for V transmitted, and then you can get when the line are having different impedances. So next, let me find out the I transmitted. The current that is transmitted at the T junction, that will be again 2 times ZC1. It was previously ZC1 plus ZL, which is your ZC2 now, times your I forward. So I forward is your this. So let me come to a fresh one. So we had seen that your V forward wave or V incident, that was, plus V reflected is equal to your V transmitted. So from here we can find out V reflected as V transmitted minus V incident or V forward. So from here I can get V reflected as VF. Previously we find out what is the formula of V transmitted. It was 2VF. It was 2VF ZC1 plus ZC2 by 2 into ZC2 by 2 minus VF. So if I take VF common from here, so what I'll be getting here is ZC2 by 2 divided by, so this will be just ZC divided by ZC1 plus ZC2 by 2 minus 1. This will come as ZC1 plus ZC2 by 2, and This will come as minus ZC1 plus ZC2 by 2. Finally, if I take the negative sign as common for reflected, so it is minus VF ZC1 minus ZC2 by 2 divided by ZC1 plus ZC2 by 2. Fine. So let us then see another special case. Let me insert here. So let's see what will happen if your line is terminated with a capacitor. So now our circuit becomes, so this is your voltage source, 2VF, this is your line with ZC, and now we have a capacitor at its end, capacitor C. So if you remember the behavior of capacitor, so initially it acts as a short circuit, and after the steady state is reached, or when the capacitor is fully charged, you can say it will act as your open circuit. This is your behavior of your capacitor. So if I find the refraction coefficient here, so basically T refraction, so that we had seen previously, it was 2ZL divided by ZL plus ZC. Now our ZL is nothing but your capacitor C. So if I write it in S domain or Laplacian domain, so ZL is basically, it was 1 by omega C. So that can be represented as 1 by CS. So if I basically replace ZL as 1 by CS, so here I will be getting 2 by CS ZC plus 1 by CS. Now let's say I have to calculate this V transmitted, basically V refracted. So that is your transmitted coefficient of refraction multiplied your V incident or your V forward. So here we are considering that this VF is a step voltage. So we represent a step voltage as UT. So basically UT is of magnitude 1. So this is your signal, a step signal of unit magnitude. If I multiply this signal with VF, basically the magnitude is now increased to VF. So this is your incident voltage, which is a step signal. So it is T refracted into VF. So let me write it as 2 by CS ZC plus 1 by CS into, it was VF into U of T. Here VF into U of T. So this will be in Laplacian domain as VF by S. Okay. So, we got V transmitted in S domain as 2 by Cs Zc plus 1 by Cs into Vf by S. So let me simplify it. So 2 Vf by S, if I take it out, so what I am remaining with basically uh, 1 by C divided by Zc plus 1 by Cs. So basically I took this one and this as common. So 1 by Cs divided by Zc plus 1 by Cs. So this can be again written as 2 Vf by S. Basically if we do the, it will be S plus 1 by Zc divided by, now finding the partial fraction of this. So this is 1 and this you will get as 1. So finally you get your inverse Laplacian you take. This can be written as 1 minus e to the power minus t Zc by C. Now once I have the expression for Vt, that is V transmitted of t as 2 Vf 1 minus e to the power minus t Zc times C. So from here, you see you have a capacitor here and you know the voltage across this is V transmitted. So what will be the I across this capacitor flowing through this capacitor? So for capacitor we know the relation is I is C dV by dt, right? So I transmitted of T is C dV transmitted by T. So if I do this, then first 2Vf it will be 0, then I have minus 2Vf, then we'll follow the chain rule basically. So we'll be getting minus 1 by Zc into C e to the power minus t Zc into C. And we had a C previously here. C times this much. So basically it will cancel out and minus minus plus, so 2Vf by Zc e to the power minus t by Zc into C. So this is your I transmitted. Now from this, if I calculate V reflected of T, so that is half of V transmitted minus IT ZC. So basically half of what was V transmitted, it was 2 VF 1 minus e to the power minus T by ZC into C minus, from here IT into ZC, you can say it is 2 VF e to the power minus T ZC into C. So 2 will cancel out from whole. VF you can take common. So you get 1 minus 2 e to the power minus T ZC times C. That is your reflected. This was in case of your capacitor. Now let us see when we terminate the line with the inductor. The third special case is line is terminated. So line is terminated with an inductor. So now what we have is similarly 2VF, the line with characteristic impedance ZC, but now it is terminated with a inductor of inductance L. So for inductor we know at t equal to 0 it will behave as a open circuit, and at the steady state it will be acting as a short circuit. So similarly, let me calculate this basically. So it was now the transmitted coefficient, or I need to find T transmitted or refracted, is same as refracted. So it was 2ZL divided by ZL plus ZC. So now in place of ZL we have inductor. So inductor is omega L, and in S domain it is SL. So I replace ZL with SL. So 2SL divided by SL plus ZC. So now V transmitted is basically T transmitted. V transmitted in time domain is basically T transmitted into VF. Similarly, this is also a step function of incidence voltage. So in S domain, so V transmitted of S, it will be 2SL divided by SL plus ZC into VF by S. So basically this is 2L SL plus ZC into VF. Basically 2VF L by SL plus ZC. So this can be written as 2VF if I divide by L. So 1 by S plus ZC by L. So now let me take the inverse Laplace to convert it into time domain. So then I'll get V transmitted of T as 2VF e to the power minus ZC by L T. So I hope this is clear. Now let us find out the I transmitted. Secondly, we have to find I transmitted. So this is an inductor now. So you know this is V transmitted. So for an inductor, you know V inductor is L di through the inductor by dt. So your DIL is V by L dt. So your IL is integration of V by L dt t equal to 0 to t. So here then I transmitted will also become as 1 by L integration 1 by omega m basically V dt. So this V is V transmitted, right? So I transmitted equal to 1 by omega L, and what was your V transmitted? It was 2VF e to the power minus ZC by L t. So this is 2VF omega is not coming here, sorry. So it is 2VF by L by yes. So it is 2VF by L integration e to the power minus ZC by L t dt from 0 to t. So if I integrate this, I get 2VF by L e to the power minus ZC by L t divided by minus ZC by L t equal to 0 to t. So I'll get IT as 2VF by L into minus L by ZC. So first let me substitute T minus ZC by LT minus, if I put T equal to 0 here, this will come as 1. So IT is minus 2VF by ZC into e to the power minus ZC by LT minus 1. Or if I take this minus to inside, so I get IT equal to 2VF by ZC 1 minus e to the power minus ZC by LT. So this is your I transmitted. So from here, if I then calculate, okay, the V reflected, so V reflected is your V transmitted minus V incident or V forward of T. So V transmitted we found out as 2VF e to the power minus ZC by LT minus VF. So this is VF 2 e to the power minus ZC by LT minus 1. So this is your V reflected. So using this formulas for inductor, capacitor and T junction, we will solve the assignment for previous year. So the first question, let me write it. Okay. So first is overhead transmission line having surge impedance. I am representing as a Z surge. ZS is 225 ohm. It is bifurcating into two branches of surge impedances. Let me represent them as ZS1 100 ohm and ZS2 of 150 ohm. So if a traveling wave of 230 kV travels along the overhead line, calculate the voltage magnitude across the first branch, that is of 100 ohms, and current magnitude in the second branch, that is of 150 ohms. Immediately after the traveling wave has reached the junction. So this is the question for T junction. Basically, this is your surge impedance of line and it is terminated with two branches of different impedances. So that is one is of 100 ohm and the other is of 150 ohms. So you need to calculate the voltage through this branch and the current in this branch. Sorry, voltage across this branch and current in this branch. So this is question 1. So let me insert one slide here. So solution 1. So we have incident voltage, that is your V forward is 230 kV and rest all things are given. So I need to calculate V transmitted. So that is 2E times your Z surge of the line plus instead of ZL we have a parallel combination of line of impedance ZS1 and ZS2. So I represent ZL with their parallel combination multiplied by ZL. So again ZS1 ZS2 divided by ZS1 plus ZS2. So ZS1 was 100 and ZS2 is 150. So the parallel impedance is 100 into 150 divided by 250. So this is 2, sorry, 4 and this is 9. So this is 50, this is 3. So 200 by 3. Wait. T is 2, 5, 30. This comes as 60 ohms. So 2 into 230. This is in kV and ZS was 225. 225 plus 60 into 60. So this I get as this is 1.614 into 60. This comes out nearly as 96.8421 kV because this was in kV, right? Now I need to calculate the current through the second branch. So I transmitted through ZS2. So basically they are in parallel. So you know this is V transmitted across both the branch 1 and branch 2. So the I transmitted will be basically V transmitted divided by ZS2. So this is 96.8421 kV divided by Z is 2 is 150. So that we get as near about 645.614 ampere. So this is your V transmitted and this is your I transmitted ZS2. And this is your V transmitted across ZS1 or which is same as V transmitted across ZS2. Okay. Then next question, let us see. Next is the same only, but here in the same information, what you are asked is calculate the magnitude of current reflected back into the line after the traveling wave has reached the junction. Basically, if I find the total supply current, that is the total voltage, incident voltage was 230 kV and the line impedance was 225 ohms. So from here I will be getting divided by 225. So this is nearly 1022.22 ampere. And previously I calculated the transmitted voltage as 96.84 kV, right? 8421, 96.8421 10 to the power 3. That was across 100 ohms. So this current comes out as, basically this will be 10 968.421 ampere. So the reflected current will be the current through the branch 1 plus current through the branch 2 minus the total supply current. So through branch 1 we calculated 968.421. Branch 2 we had calculated previously. It was 645.614. 645.614 minus 1022.22. So this comes out as 968.421 plus 645.614 minus 1022.22, 591.815 ampere. So that is the magnitude of current reflected back. This is your answer. So let us move to the next question. So question 3. Which of the following statement is correct? Which of the following statement is correct? When a rectangular surge travels along the line is terminated by inductance. Is terminated by an inductance. So first is the voltage across inductor I represent as VL initially decreases to double the value of the incident wave and increases exponentially. The second one, so it is showing the VL initially rises to double the value of incident wave and decays exponentially. Third says the inductor initially acts as a short circuit and is charged through the line impedance Z. D is any of them. Let us discuss this first in detail. Let me insert a new slide. So if you remember, we derived the condition, special condition for line terminating with inductor, right? So there we discussed the inductor initially at t equal to 0. So, so this was the case of line terminated with inductor. So we discussed here that initially it is acting as open circuit and finally it will act as short circuit. So initially it is open circuit and finally this will behave as a short circuited transmission line. And we also derived the expression for voltage here. So V transmitted was 2Vf e to the power minus ZL Z by LT. So V transmitted was 2Vf e to the power minus Zc by L times T. So Vt at t equal to 0, what will be this Vt? If I put t equal to 0 here, so this will come as 1. So this will be Vf. And what about at steady state or at t equal to infinity basically? So this will come out as 0 e to the power minus 6. So basically if I draw the voltage across inductor and time, so at t equal to 0, this is at 2 times of the incident voltage, and after varying long time it will exponentially decay to 0. So let us see what options are given. So it is saying VL initially decreases to double the value. So decreases to double, this is wrong, and it is also saying it is increasing exponentially. But here we can see it is a decreasing exponentially, and basically incident was V, but when it is terminating with inductor, the voltage is increasing to first to Vf and then exponentially decreasing to 0. So the second option says V across the inductor initially rises to double of incident. So this is Vf basically. Yeah, so this is Vf basically, and then it is decays exponentially to 0 at t equal to infinity. So this is the correct one. Third one says inductor initially acts as short circuit and charged through the line impedance ZC. So this is again wrong. We had seen that it initially the inductor will act as open circuit, and so that the voltage is increasing to t 2 times of the incident voltage, and finally or at t equal to infinity or at steady state it acts as short circuit so that the voltage decays to 0. So I hope this was clear. So t equal to infinite. Now let us go to the next one. So the next question says an 115 kV rectangular surge wave travels along the line terminated by an inductance of 12.5 millihenry. Determine the magnitude of voltage across the inductance after 15 microseconds. If the surge impedance of line is 225 ohm. So here we have given the surge impedance of line is 225 ohm, and after how many 15 microseconds, 50 is 15 microseconds, and the incident voltage magnitude Vf, it is given as 115 kV. So we have seen the formula for E transmitted in case of inductor previously, right? How much it was? 2 times of Vf e to the power minus Zc by Lt. So 2 times of Vf e to the power minus Zc by L times T. So here the characteristic impedance of line is same as the surge impedance given as 225. So 2 into 115 e to the power minus 225. L is given as 12.5 millihenries. 12.5 into 10 to the power minus 3 millihenries. T is 15 into 10 to the power minus 6. So solving this will get 2 into 115 into e to the power of minus 225. 12.5 into 10 to the power minus 3 into 15 into 10 to the power minus 6. So that is coming out as 175.5772 kV. Right, we derived this formula. So let us then move to the next one. So next is question number 5. It is saying as same thing, 15 kV rectangular search travels along the line terminated by inductance of 12.5 millihenries. Then determine the magnitude of reflected voltage after same 12.5 microsecond. If your ZC or ZS is given as 225 ohms. So here we need to calculate V reflected, right? So this also we had derived the expression. Let us check what it was. So V reflected was VF into 2 times of E ZC minus ZC by LT minus 1. Okay, so it is 2 times of VF 2 times of E to the power minus ZC by LT minus 1. So again, so V reflected will come as 115 2 into e to the power minus 2 to 5 divided by 12.5 into 10 to the power minus 3 into 12.5 into 10 to the power minus 6 minus 1. So this will come out as 115 into 2 into e to the power this into 2. Sorry, this is changed. This is not 12.5 microseconds. Minus 1. So this will come out as 68.66 into 10 to the power 3 volt. Right. Now let us move to the next one. So the voltage in kV of 2.45 per unit BIL or basic insulation level, basic impulse insulation level for a 240 kV transmission line is So if you remember, for the insulation level, we always calculate the peak, right? Maximum or peak value of voltage we need to calculate here. So it is 240 kV in per phase. So I divide by root 3. This is an RMS, and then I convert into peak by multiplying by root 2. So this is for 1 per unit, and since it is given as 2.45 per unit, so multiply again by 2.45. So this we get as 240 divided by root 3. This is going to give us 480.09, or 1, we can say it as 1 kV. Okay, then let's move to the next question. So next is question 7. Is saying that 165 kV 4 microsecond rectangular surge on a line having surge impedance 350 ohm approaches a station at which the concentrated earth's capacitance is 25 nanofarad. Then determine the magnitude of reflected voltage wave. So here we need to calculate it reflected. So E reflected will be E total, or E transmitted minus E incident. So we have calculated it earlier, the formula for line terminating with the cable minus T ZC C minus the incident, right? So this is your incident, or V forward. This is incident. Previously for cable we had derived it was 2VF 1 minus e to the power minus T by ZC. So that one minus this formula also we had seen previously. So just we need to put the values here. So the incident is 165 kV. So if you see, finally we had the formula of V reflected as this one. If I take that as common, so that was So here, from here, if I, so 2 into 165 into minus e to the power minus ZC is 350 and this is 25 nanofarad. So I think the information is given here at t is 4 microsecond. So here I get 4 into 10 to the power minus 6 minus 165. So if I calculate this, so that is e to the power of minus 4 into 10 to the power minus 6, 350 into 25 into 10 to the power minus 9. So 1 minus this 2 into 165. This is 121.0803 minus 165. That is coming out as minus 43.92 kV. So finally your E reflected is minus 43.92 kV. Okay, next one. This was 7th, then 8th. Question 8 is same as above. Similarly, 165 kV. 4 microsecond was given here basically previously also. So 165 kV, 4 microsecond, rectangular surge having surge impedance same 350 ohm and the capacitance is 25 nanofarad at the station. So here it is asked as transmitted current into capacitor. So here, so I transmitted, we had calculated that also. Yeah, this is I transmitted is 2 VF ZC, 2 VF by ZC. right? V, this is inductor. Yeah, 2Vf by Zc. So 2 into 165 Zc is 350 e to the power minus 4 into 10 to the power minus 6 of Zc is 350, C is 25, 10 to the power minus 9. So this one will get us e to the power minus 4 into 10 to the power minus 6 by 350 into 25 and 10 to the power minus 9 into 2 into 165 divided by 350. So in kilo amps, so this is coming near about 0.5969 kilo ampere or 596.9 ampere I transmitted. Right. Then next question. Question number 9. So here it is saying a transmission line with surge impedance 225 ohm has a terminal load consisting of parallel combination of capacitor and resistor. Basically C is 0.05, 0.055 microfarad, and R is 4.5 kilo ohm. So a surge voltage in form of unit step of 220 kV travels along the line then find the load voltage 7.5 microsecond after the arrival of wavefront of surge. So basically surge impedance or ZC or ZS, whatever you call it, is given. Characteristic impedance or surge impedance that is given, and it is terminated with a parallel combination of R and C. Their values are also given. The incident voltage magnitude is given to 20 kV. So it is telling that find the load voltage after 7.5 microsecond. So first we will here calculate the coefficient. So T will be So basically this will be ZC into R, ZC plus R into E. So if you put the values here, you will get as 225, 4.5 into 10 to the power 3, 225 plus 2, 3 into, so into C. C is 0.055 nano. This is coming out as 11.79 to power minus 6. This is C basically. So for load voltage or transmitted voltage basically, into 1 minus e to the power minus, so here initial transmitted is R plus ZC. So this will come out as 419.5 kV. T is 7.5 into 10 to the power minus 6. Tau is 11.79 into 10 to the power minus 6 kV. So this you'll get as 197.29 kV. Okay, next one, which of the following is or are necessary to determine the line insulation level for a transmission line of 1000 kV. So switching surge, lightning surge, so A is only 1, only 2, both 1 and 2. D cannot be decided. So here you can see, can you tell what will be the answer? The transmission line is of 1000 kV and it is a high voltage line. So how the insulation level is decided for such kind of line? On which factor will it depend? Switching surge or lightning surge? You can also type in the chat box. So this is an extra high voltage line, right? So its insulation level is decided on the basis of switching surge or lightning surge. So for lower voltage line and for higher voltage line. So here the lightning surges are more prominent, or you can say lightning surges are greater than the switching surge. So here insulation level is decided on the basis of lightning surge. However, for high voltage line, the switching surges are even greater. The yeah. So as I was saying here, lightning surges are used to determine the insulation level for lower voltages. But in case of high voltage line, the switching surges are very high. So here, when the voltage level of the line increases, gradually we can say the insulation level it is being decided on the basis of switching surge. But for low voltage line, the switching surges are not of significant magnitude. So here lightning surges are used. So since 1000 kV is coming under EHV, so basically here we'll decide it on the basis of switching surge. This is only A. So we have time. I think we can solve some more questions also. So if you remember, so which this one only. So next question. So which of the following is correct? Is correct when a rectangular surge travels along the line terminated by an capacitance. So first one is initially voltage across capacitor decreases to VF. VF, let's say it is the incident. This rectangular surge is of magnitude VF and exponentially increases gradually. Second is initially voltage across capacitor increases to 2 VF and then exponentially decreases. Third one, initially behaves as open circuit and then at steady state it behaves as short circuit, or last one, all. So this is again for line that is terminated with a capacitor, right? So he had seen the voltage expression for this case by capacitor. So this V transmitted was 2 VF 1 minus e to the power minus t by ZC times C. So basically the voltage across this capacitor same as the transmitted voltage expression, that is 2 times the incident voltage 1 minus e to the power minus t by Zc into C. So similarly at t equal to 0, the expression for V capacitor, it will be, if I put t equal to 0, so this will be 1. So 1 minus 1, it will be 0. At t equal to infinity, the V capacitor, so then it will be 2 times of Vf, and we know the capacitor behavior. So at t equal to 0, it will act as short circuit instantaneously, and gradually when it will be charged at t equal to infinity or at steady state, it will act as open circuit. So similarly, if I draw in case of capacitor the voltage versus time, so initially it is 0 and gradually it will charge to 2 VF. So this is the solution for 11. So I think I have to reframe the options here. If I say initially decreases to 0 and exponentially increases. So this is the correct. Initially it is 0 at t equal to 0 at t equal to infinity. So initially it decreases to 0 and then exponentially increases gradually. We can add 2 times of the incident. So this is correct. This is wrong, same. So answer is option 1. Now let us solve one more question. So let's say the incident voltage of the surge is 115 kV rectangular surge, and let's say the capacitance is 2.5 nanofarad. So determine voltage across capacitor after 15 microsecond if the surge impedance of line surge impedance is 225 ohm. So if I calculate here, we had seen the expression here now, the previous one only. It was 2Vf 1 minus e to the power minus t by ZCC. So it is 2Vf 1 minus e to the power minus t by Zc into C. So basically it will be 2 into 115 into 1 minus e to the power minus 15 into 10 to the power minus 6. Zc is 225. C is 2.5 into 10 to the power minus 9. So if I calculate this, e to the power minus of 15 into 10 to the power minus 6, 225 into 2.5 into 10 to the power of minus 9. So 1 minus answer 15 into 10 to the power minus 6. This is coming out about to be 230 kV. So this is the transmitted voltage. Now again, if I calculate for the same question, question 13, for question number 12, calculate reflected voltage after same 15 microsecond. So for reflected voltage, the expression was V reflected was Vf 1 minus 2 e to the power minus t Zc times C. This is 115. 1 minus 2 into e to the power minus 15 into 10 to the power minus 6. This is 225. C was 2.5 nanofarad. So this will come out as 115 kV. Right. And then let us solve another question. So we had, let's say this Surge impedance of line is 225 ohms and it is bifurcated into two lines of 100 ohms and 100 ohms. So calculate the transmitted voltage and current in each branch. So here this is 14. So basically the V transmitter will be 2E incident divided by ZC plus their parallel combination, right? Into ZL. So ZL is here, parallel combination of these two. Or we can say it is simply by 2, right? Because they are same. So transmitted voltage is not given yet. Let the incident voltage be 230 kV. So 2 into 230 225 plus 50 into 50. So that will come out as 2 into 230 divided by 225 plus 50 to 50. So 883.63 kV. And what about I transmitted? That is V transmitted divided by 100 ohms. So that will come out as 0.8363 kiloamps or 0.3 ampere. So here you can see the current will be equal 36.3 ampere. Here also same, and the voltage transmitted, that is 83.63 kV. And let us solve one last question. For the same question, for question 14, calculate reflected current so we calculated the current through Z1 is same as current through Z2, that was 836.3 ampere. And what about the total current? That is 230 kV divided by the surge impedance of the line 225. So that will be near about 22.2 ampere. So the I reflected, it can be calculated as 2 into 836.3 minus the I total. So that comes out nearly 2 into 650.38 ampere. So I think we'll stop here. So I hope this was clear. If you have any doubts, we can answer, or else we'll close the session and we'll meet in the next week for discussions on the next week. So I hope this week's assignment they were clear. Basically, this week assignment it was on this at for T junction or when the line is terminated with capacitor. So we derived the formulas. When the line is transmitted with a capacitor, what will be the transmitted current, reflected current, and transmitted current, all those. Then the third special case we saw when the line is terminated with an inductor, and we calculated or derived the expression for those also. So only these three, using these three formulas, you can solve the assignment for this week. So I think this all are clear. So if no doubts are there, I think then we may close the session for today. So thank you for joining, and we'll meet next week at again Saturday 3 p.m.